Welcome back, everyone. I'm Akash Joshi. I'm the Operations Research Guru, and today I'm going to teach you how to solve the hospital location problem. Okay, so we have a bunch of cities or densely populated areas in a country or a big city or something like that, and we're trying to put a hospital in the right place so that it covers the most amount of people and a lot of people have access to the hospital so that way the hospital can save more lives. But the problem is we don't know where to put this hospital so that we can optimize the number of lives that it saves. So that's where an operations research analyst comes in, and we create a mathematical model to find out where to put the hospital so that it saves the most number of lives. Do we put it here, 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 here? Where do we put it, right? So right off the bat, you might think, hey, we want to put it right over here because there's a lot of population right over here. So that way, if you put the hospital over there, it'll save a lot more lives. And you're absolutely correct, but we also want to save lives over here, over here, over here. And I talked about that in a different video called the facility location problem video. And that video got over 100 views. So if you want to watch that, then go ahead and watch that. But in this video, we're going to try a different method of solving the hospital location problem. And we're going to focus on a specific way rather than last video when I talked about 3 different ways. Okay. So we're going to use 2 distances to solve this problem. We're going to use Euclidean distance, which is your typical distance formula, straight line between 2 points. And we're going to use Manhattan distance, which is basically perpendicular lines. So say we have this city and this city, the distance would be this right angle right here. So this could be 3 units, and this could be 2 units. And the total Manhattan distance between those 2 points would be 5 units. Okay, now that we talked about the distances, let's get down to the formulation. Okay, we're minimizing the total distances between all of these nodes and the hospital. Of course, we don't know where we're going to put the hospital, but the computer is going to do that. It's going to try a bunch of different places to put the hospital, and it's going to find the one. It's going to find the coordinates of the hospital that minimizes the total Manhattan distance to that hospital. And the way we do that is we just set up this formulation. Let's talk about the formulation. Okay, so I equals 1 is like the lower bound of the summation, and n is the upper bound of the summation. N is the number of cities. I equals 1, that's just the first city. You can pick any city to start with. And basically what the summation is going to do is that it's going to plug in the coordinates. So for the first city, x1 and y1, those are the coordinates of the first city. It's going to say the coordinates of the first city were like 3, 5. Then it would do x minus 3 plus y minus 3, the absolute values, those quantities, of course. And it's going to try to minimize that. It's not going to try to minimize that distance, but it's going to add up all the other cities' distances too, and then it's going to try to minimize that by adjusting the coordinates of the hospital. Okay, so that's the formulation for the Manhattan distance. And the Euclidean distance works the same way, except instead of the absolute value of the x coordinates and the absolute value of the difference of the x coordinates is added to the absolute value of the difference of the y coordinates. It's just going to be your typical Euclidean distance, square root of 2 quantities added together, which are squared. And we're, of course, minimizing the total distance between all of the nodes and the hospital. Okay, so you plug that into your computer and you get the answer. You don't have any constraints. And yeah. One thing to keep in mind is that this is a nonlinear program, and that means that it's still going to require a lot of time for your computer to solve because nonlinear programs are tricky. And you know it's a nonlinear program because there are absolute value signs in this formulation, and there's a square root and squared signs in this formulation, which all of those make a program nonlinear. Okay, and if you didn't know, NLP stands for nonlinear program. So now let's talk about linearizing the Manhattan distance formula. Not the Manhattan distance formula, the Manhattan formulation that I've created. Let's talk about linearizing that so our computer can give you an answer in a matter of seconds. Okay, to linearize it, one sec, let me just fix a typo. This is supposed to be a B, not a V. Okay, So to linearize it, we're gonna, this is the old formulation. We're minimizing that. But we want to try to get rid of this absolute value signs. And our goal is to just substitute a variable for this and a variable for that. We can't do that. We can't just say AI is equal to this absolute value and BI is equal to this absolute value. Because if we just did that and made the formulation this, we still have absolute value signs in our formulation because AI and BI have to be something, right? They have to be the absolute value of something, and absolute value signs make a program nonlinear. So we still have to linearize it. And the way we do that is we use inequalities. Let me write one thing just so you don't get confused. This is a goal. We're trying to set AI equal to x minus xi, the absolute value of that, and we're trying to set BI equal to absolute value of y minus yi. That's the goal, but we're not going to be able to just write that in our formulation because it would still be nonlinear. So the way we linearize it is we make absolute value functions, not absolute value functions, inequalities. So we have AI, right? We set AI greater than x minus xi, and we set AI greater than or equal to xi minus x, which is just this flipped. And if we just flip it around and set them greater to or equal to, greater than or equal to, then that's practically the same thing as an absolute value function. And we do the same thing for BI. So this right here is our formulation for linearizing. Let me just mark it off. That is our complete formulation for linearizing the Manhattan distance hospital location problem. Okay. Now let's talk about linearizing the Euclidean distance formula. Guess what? You can't linearize it because it's too complicated to linearize. There's a square root function, and then there are terms that are squared in between that are being added together. So there's really no way to linearize the Euclidean distance hospital location problem. You're just stuck with this nonlinear program, and you'll have to stick it into your computer so that your computer can solve it, and it might take a little while, more than a few seconds for your computer to solve it. What if we wanted to add some constraints to the Manhattan distance formulation that we created on the previous page? Let's say we want the distance between the hospital and the center of the country or the city. Let's say we want that distance to be less than 50 units. That way, if the hospital is somewhere around the center, we can these population nodes can still reach the hospital. Okay. So we want that constraint added to the formulation. How do we represent that constraint mathematically? This is our formulation, and this is our constraint expressed mathematically. Let's talk about it. Let's call the coordinates of the center z, w. Z is the x coordinate, w is the y coordinate for the center. And let's talk about how I even got this center. The center is not always going to be the origin because your city might not necessarily be at the origin. Your city could be like somewhere over here because cities aren't perfect circles, they're just blobs kind of. So I estimated the center to be over here somewhere. It's kind of like the center of your country or center of your landmass or center of your city, however you want to think about the center. Okay, so the center is just represented by the coordinate zw. For the x coordinate, z minus x, x is the x coordinate of the hospital. And for the y coordinate, w minus y, y is the y coordinate of the hospital. And we're going to add those two quantities together because that's our Manhattan distance. And that Manhattan distance has to be less than or equal to 50 because we want it 50 units. We want the hospital within 50 units of the center. And for 50 units, you might be thinking, why not 50 miles? Why not 50 kilometers? Because it all depends on the coordinates. If the coordinates of your graph are represented in miles or meters or kilometers or whatever, if you're that's basically what this 50 is going to mean. It's either going to mean 50 miles if your coordinates are miles. It's going to mean 50 meters if your coordinates are meters. That just depends on your preference and the problem that you're making or solving. Okay, so all we have to do is add this constraint to the formulation. We enter it into the mathematical model, and the mathematical model spits out the correct optimal solution, and that optimal solution will be in the form of coordinates. And using those coordinates, we know where to build our hospital, and that hospital will save a lot of lives And yeah, that's it. So thank you for listening. Thank you for watching my video. See you next time. Goodbye.